Section 7.3 has 3 parts, part 1, 2, and 3. And all 3 of those parts deal with volume of various solids on graphs. So part 1 deals with volumes with regular cross sections, and we're thinking of volume as the area times thickness. So in this section we're looking at building solids on top of the graph that we have. So for example, for this particular graph, we want to build a solid of isosceles right triangle cross sections on top of this region bounded by the x-axis, the y-axis, and the curve y equals square root of 4 minus x. Okay, so that's the base. That area, that shaded area, is the base of our solid, and now we're going to build various isosceles right triangles on top of that, with the base of that right triangle being whatever slice of the area we have in our graph. Okay, so these cross sections are perpendicular to the x-axis. Okay, so that means that x is our variable. Alright, so if we're looking at this graph and we want to create isosceles right triangle cross sections. So an isosceles right triangle has 2 sides that are the same, correct? So if we look at this, that means this side and this side will be the same for that triangle. This side and this side will be the same for that triangle. So if we're looking at this side being h, right? H is the length from the x-axis to my graph, my line of my graph. So h is the square root of 4 minus x. And since h and b are the same, that is also going to be the square root of 4 minus x. Okay, so now what we want to do is we want to find the area of the right triangle, because all of the areas of those triangles added together will give us the volume of the solid that we've created. So we're going to find the area of our isosceles right triangle. We know area of a right triangle is 1/2 base times height. So we'll have 1/2, and our base is square root of 4 minus x. And our height is also square root of 4 minus x. And when we simplify this, since these are the same and we're square rooting them, it's as if taking square root of 4 minus x squared. So we have 1/2 times 4 minus x, which is just 2 minus 1/2 x. So that's the area of one of our isosceles right triangles. Okay, that's how we find the area for one of them. So now to find the volume of the solid, we're going to integrate so that we're adding up all the areas of all the possible triangles that can be created in this space. So to find the volume of this solid, our limits of integration go from 0 to 4. And we're looking to find we're looking to integrate the area in terms of x dx for each one of those triangles. So our volume is going to be from 0 to 4 of 2 minus 1/2 x dx. Okay, and so this problem is asking us to write and solve. So we'll go through the entire process. We'll integrate this. So v is equal to 2x minus 1/4 x squared. And we're integrating from 0 to 4. So that gives us v is equal to 8 minus 4, which is 4. So the volume of the solid that we would create if we drew a bunch of isosceles right triangles on that shaded area being the base is 4. So now let's look at what would the volume be for different shapes. So now let's look at where we have a base, that's our shaded area. And now we're building a whole bunch of equilateral triangles on top of it, and those are going to be our cross sections. So we're building this solid, and if we slice it open, then the shape of that slice would look like an equilateral triangle. That's where the word cross section comes from. So the solid is built on a base bounded by the x-axis and the curve y equals sine. So x-axis and the curve y equals sine x on the interval from 0 to pi. The cross sections are perpendicular to the x-axis, so that means that x is the variable. And the cross sections are all equilateral triangles, so all the sides of these triangles will be the same. If you wanted to see this digitally, you can type in that website and it'll bring you to a digital kind of GIF of what that would look like. For those of you who are a little bit more visual and need to see what this problem really means visually, you can do that. So now looking at this problem, right, all these sides will be the same because we have an equilateral triangle. And if we look at our graph, one of those sides we can definitely say is the length from x to our graph, which is y equals sine x. So that means s is equal to sine x. Now for those of you who do not know, the area of an equilateral triangle is equal to s, being the side, squared over 4 times square root of 3. That's actually the formula for finding the area of an equilateral triangle. So with that, we know that our area for just one of these equilateral triangles is going to be sine x squared over 4 times square root of 3. Now this problem is only asking us to write an integral that represents the volume of the solid that would be created, right? So we know we're going to take the volume, and to do that we need to integrate our area of x dx, and it tells us from the problem that our interval is from 0 to pi, so we're going from 0 to pi. So therefore, to write this integral, I'm just going to replace the area of x with our area equation. So volume is equal to the integral from 0 to pi of sine squared x over 4 root 3 dx. And there's our volume integral. Okay, so let's look at another type of cross-section. So for this one, we're looking at a square cross-section. Okay, so our cross-sections are going to be squares. And we're looking for the region bounded by the graphs f of x equals 2x squared minus 6x plus 4, and g of x equals 4 cosine 1/4 pi x. So we're looking for the region between these two graphs. So this was actually an AP question back in 2013. So we're looking for this space in here. All of that space. I didn't want to color over the squares, but all of that space between those two graphs. So first thing we want to do is identify which graph is which. So my knowledge of cosine tells me that it'll start here and it will drop and then come up and then drop and then come up. So with that, I know that my top is actually y equals 4 cosine 1/4 pi x, which means that our bottom graph is y equals to x squared minus 6x plus 4. So then, to find the length of one side of the square, the length of one side of the square is going to be our top function minus our bottom function, right? Our upper minus lower. So then we have our upper function, which is 4 cosine 1/4 pi x, minus our lower function, which is 2x squared minus 6x plus 4. And we know how to find the area of a square. Right? The area of a square is just side squared. So the area of the square is just 4 cosine 1/4 pi x minus 2x squared plus 6x minus 4 squared. If you wondered why I changed the signs, all I did was distribute this negative sign. Okay, so then to find an integral expression that gives you the volume of a solid, right? We know volume is going to be equal to the integral. For this problem, we're going from 0 to 4 since we're in terms of x. So from 0 to 2. So 0 to 2 of whatever the area equation is that we found. So v is going to be equal to the integral from 0 to 2 of 4 cosine 1/4 pi x minus 2x squared plus 6x minus 4, all of that squared, dx. Okay, so now let's look at cross sections, but now we're going to be focusing on these cross sections being perpendicular to the y-axis. So when they're perpendicular to the x-axis, x was our variable, but now they're going to be perpendicular to the y-axis, so now y is going to be our variable. So for this solid that we're building, the base of the solid is the region enclosed by y equals e to the x, and the lines y equals 1 and x equals ln of 3. Cross sections are perpendicular to the y-axis and are squares. So perpendicular to the y-axis, so y is the variable. Okay, so because y is the variable and our equation is in terms of x, right? We have y equals e to the x. So in this statement, x is our variable, right? We plug in something for x, we get y. We want y to be the variable, so we actually have to solve for y here. So in order to do that, we'll take the ln of both sides to get rid of the e. So we have x is equal to ln y. So now we'll plug in a y value and we'll get an x answer. So now y is our variable. So this is what we want. We want to use this equation because y is going to be our variable. So our next point to make is which graph is top function, which line is the bottom function, which line is which, right? So we know that y equals 1 is a line. So y equals 1, pretty simple. We also know that x equals ln 3 is a line. So x equals ln 3. ln 3 is a value, it's a number, so it's going to be a straight vertical line. So this is x equals ln 3. And then the last line that we know is that y equals e to the x, right, which we rewrote as x equals ln y. So we'll rewrite this as x equals ln y. Okay, so we found the lines. We need to find where they intersect, because we also, when we write our integral, need to know the intervals for integration, right? So they intersect in 3 places. We need to know what those 3 places are. So here, this line will always be ln 3, this line will always be 1. So x is ln of 3, y is 1. And then up here, this line is ln of 3, this graph is ln of y, and if they intersect here, that means y is equal to 3. So we have ln 3, comma 3. And then down here, we're on the y-axis, so we know x is 0, and we know y is 1. So we have our 3 points of intersection. So, given that this is the area of our base of this solid, and our squares are perpendicular to the y-axis, so that means that this side is the side that we're actually able to find values for. And this side is the length of the right, the boundary on the right, minus the boundary on the left. Boundary on the right is ln 3, the boundary on the left is ln y. So we're going right minus left. So we have ln of 3 minus ln of y. That's the length of one side of the square, which means it's the length of all the sides of the square. So the area of our square is equal to s squared, which is ln of 3 minus ln of y squared. So if we want to write an interval for this, we have to remember that our variable is y. So our limits of integration need to be the y values, right? So our lowest y value is 1, our highest y value is 3. So we're going from 1 to 3 of the area of y dy. So we have the integral from 1 to 3 of ln 3 minus ln y squared dy. All right. Now let's look at semicircles. So we're building a solid on a base that's going to have semicircular cross sections. So a solid is built on a base bounded by the x-axis and the line x equals 9 and the curve y equals square root of x. Cross sections are perpendicular to the x-axis. So x is the variable. Okay. So if you want, again, a more visual look at this problem, you can type in that website and it'll give you more of a visual 3D understanding of what this problem is asking. Okay, so here's our semicircle. We're looking at this space here. Okay. So since x is our variable, we're going from 0 to 9. And to find the area of a semicircle, actually going to write that first. The area of a semicircle is equal to 1/2 pi r squared, right? So we need to find r. R is from the center down, and we know that this line here is y equals square root of x. So r is only halfway from x to our line y equals square root of x. So r is only 1/2 of square root of x. So when we plug that in, we have the area of our semicircle equal to 1/2 pi 1/2 root x squared, which is equal to 1/2 squared is 1/4. Square root of x squared is x. 1/4 times 1/2 is 1/8. So I have pi over 8 x is the area of our semicircle. And now, again, to find the volume, our limits of integration, since we're in terms of x, go from 0 to 9. And we're going to use the area that we found above. So v is equal to the integral from 0 to 9 of pi over 8x dx. And this is asking us to also solve. So when we integrate that, we get pi over 8 x squared over 2 from 0 to 9. Which is equal to 81 pi over 16. Now we'll look at this similar problem, but now with our cross sections perpendicular to the y-axis. Okay, so if our cross sections are perpendicular to the y-axis, then y is the variable. We have volume of a solid whose base is a triangle bounded by the x-axis, the y-axis, and the line 2x plus y equals 2. So we have 2x plus y equals 2. So if y is our variable, then we want to solve for x, because we want to input a y and get out an x. So if we do that, subtract y, so 2x is equal to 2 minus y, divide by 2, so x is equal to 2 minus y over 2. So I'm going to rewrite this line as x equals 2 minus y over 2. And then we can just find points of intersection. So up here we know the y-intercept of this line is going to happen at 2. So this is 0, 2, and down here, this is 0, 0. And the x-intercept happens at so this is 1, 0. Okay, so now we're looking at semicircle cross section. So again, the area of a semicircle is pi r squared. Oh, 1/2 pi r squared. Sorry. So the area of a semicircle is 1/2 pi r squared. R is half the distance between the y-axis and our equation 2 minus y over 2. So R is equal to 1/2 of 2 minus y over 2, which is equal to 2 minus y over 4. So the area of our semicircle is going to be 1/2 pi 2 minus y over 4 squared. Which is equal to pi over 32 times 2 minus y squared. Okay, so now to write and solve the integral that represents the volume of this solid. So to write it, we know that volume is going to be equal to our limits of integration need to be in terms of y, so 0 to 2. And we're finding our area in terms of y dy. So our volume is going to be from 0 to 2 of pi over 32 times 2 minus y squared dy. If we integrate that, c is equal to pi over 32, 2 minus y cubed over -3, from 0 to 2. Which is equal to 8 pi over 96, which is pi over 12. And that concludes part 1 of section 7.3.